Welcome back. Today we're going to look at section 6.5. This is really actually a very short section. There's not a lot that we're going to worry about in this section. It's just another application of antiderivatives. Remember, that's what we're doing for this whole chapter is applying integration techniques, applying antiderivatives. And so we're going to look at lengths of curves. I'm going to go through this in a little bit of detail for now, and then we'll when we get to the end, we'll just look at a few examples and see that it's really just a matter of remembering a formula and remembering how to apply that formula to a given situation. Okay, so here's the idea. Our goal is to say here's some curve given by a function f at x, and I would like to know how long is that curve between 2 points, A and B? What is the length? If I were to actually walk that path, how far have I walked? That's the goal. That's the idea. But our idea, remember, the idea always in calculus is to break things up and calculate them in a simple way by approximating them, and then adding up our approximations. Take a limit as the number of our approximations goes to infinity, so the error goes away, and we actually get a final accurate result in the end. So what we're going to do to approximate this length is to say, all right, rather than walk along a curve, we can approximate this by walking along a straight line and then walking along a straight line. Finding lengths of straight lines are very easy, right? We just calculate the length of the line. So that's one approximation of the distance traveled. A better approximation would be following two, maybe three lines rather than just two. And then 4, then 5, then 10, then a million, then a billion, and an infinite number of lines. By taking a limit, we're going to get the actual length of the curve. Now, that said, let's notice that when we get more and more approximations here, if I put 3 in here instead of just 2, the idea here is that these lines that we're using to approximate the distance along the curve follow pretty closely the tangent lines of the curve. So if I would use the tangent line here or the tangent line here, I get something that's very close to what we actually need. And so if I follow my tangent lines, I get a pretty good approximation as well. And so this is our idea. We're going to follow the tangent lines for a given distance. So let me make a different picture. So suppose that here's A and here's B. And I said, all right, here's my tangent line. And let's calculate the distance of the tangent line between A and B instead of the distance along the curve. That's pretty easy to do because the tangent line, this is the point A, f at A, and the slope of this is f prime at A because the derivative gives us the slope of the tangent line. So I have the slope and I have a point. So the equation of this line is y minus the y value is m times x minus the x value. That's the point slope form. So that's y minus f at A is the slope, which is f prime at A, x minus A. This distance is b minus A. So this distance is b minus A, and let's call that delta x. So this distance is delta x. This distance, then, we can get, so if I want to know this, let's call this delta y. And we're going to figure out what that is in terms of everything else. The idea here is that delta y over delta x is exactly the slope of the line, f prime at A. So that delta y is f prime at A times delta x. All right, so now what's the distance of this tangent line between this point A and this point B. Let me keep this part up here. Delta y is f prime at a delta x. And so the distance is really just a Pythagorean theorem. The distance is the square root of delta x squared plus delta y squared. And that's the distance along the tangent line. But that's the square root of, according to what we've got here, delta x squared plus f prime at a squared times delta x squared, because that's delta y. Now I'm going to factor a delta x squared out, and if I factor a delta x squared out, let's put it on the right, I get 1 plus f prime at a squared and then multiplied by delta x squared. But if I square root a square, I get back to where we started, so this becomes square root of 1 plus f prime at a squared times delta x. And that's the length along the tangent line if we move from A to B and the distance is delta x. All right, now I'm not going to go through all of the details of creating a Riemann sum here, but suppose that we used 2 tangent lines instead, or 10 tangent lines, or we broke it up into 100 different small line segments rather than walking along the curve. Each of those line segments has a length given by that exact same formula, where A no longer is the very beginning, but it's the beginning of the line segment instead. And what we get is a sum of the square root of 1 plus f prime at, so A is not my beginning, we're going to call it x sub I, where x sub I is the beginning point of my line segment, squared, and then multiplied by delta x, and then I have this sum where I goes from, in this case, I'm not going to really be too worried about these details, but remember Riemann sums, if we have a left Riemann sum, it starts at 0 and goes to n minus 1, so that we have a total of n terms. But really, in the end, what we need to remember is that when we take a limit of this, as n goes to infinity, that is, as the number of line segments goes to infinity, this becomes an integral. A limit of a sum is an integral. And so this is just square root of 1 plus f prime at x squared. When we go to an integral, delta x becomes dx. And then when we integrate, we're going across the entire x region in question, which is going to be A to B. And this is really all we need to, in the end, remember and be able to apply and use when we're talking about lengths. So this formula gets me the length of any curve given by the function f at x between A and B. That gives me that length. So let's apply that to a few examples and see that it works. And then apply it to some where we couldn't actually do another way. Suppose that I had a circle of radius 1, which is x squared plus y squared is equal to 1. Well, this means that y is equal to the square root of 1 minus x squared. But that's only going to give us the top half of the circle. Really, it's a plus or minus. But let's only look at the top half, the plus version. And let's ask, what is the length? So this is minus 1, and this is 1, because it's a circle of radius 1. Let's apply our formula and come up with the length of that curve. We already know what that length is, because we know what the circumference of a circle is. But we want to make sure our formula actually works. So the length will be the integral across the x values in question, minus 1 to 1, square root of 1 plus y prime squared dx. Well, y prime is Well, this is 1 minus x squared to the 1/2, so I get 1 minus x squared to the minus 1/2. So the 1/2 comes down, the exponent gets lowered by 1, and then we need to multiply by the derivative of the inside, which is negative 2x. So the 2's cancel, and I get 1 minus x squared to the minus 1/2 multiplied by negative x. So when I square that to put it into here, I get minus 1 to 1, square root of 1 plus, if I square this whole thing, so remember this is really in the denominator, so if I square this, I get x squared in the numerator, the negative goes away, x becomes x squared. When I square the denominator, it becomes 1 minus x squared. But we can actually simplify this integral, minus 1 to 1. If we add these two things up that are underneath the square root, that's 1 minus x squared over 1 minus x squared, if I turn this into a common denominator. So I get square root of 1 minus x squared, then plus x squared over 1 minus x squared by making the common denominator, dx. But this is integral minus 1 to 1. The numerator now just simplifies to 1, and the denominator is 1 minus x squared. Minus 1 to 1. If I square root the numerator, I get 1. The square root of the denominator is 1 minus x squared dx. Now this is something that we've seen before. We saw this in our trig substitutions. This is a sign substitution. 1 minus x squared is a sign substitution. As it turns out, I'm not going to go through the whole process, but we get sine inverse of x. So sine inverse of x is the antiderivative, which is good because we started with a circle, so getting some trig stuff is not that surprising, evaluated from minus 1 to 1. And so if we plug in 1, I get sine inverse of 1 minus sine inverse of minus 1. But sine inverse of 1 says what angle gets a y value of 1? Well, that's pi over 2. What angle gets a y value of minus 1? Well, that's negative pi over 2. When we add these things up, I get pi, which is great because we wanted the length of a half of a circle, but the length of a whole circle is 2 pi. So the length of half the circle is pi, and our formula recovers what we wanted to recover. Now, let's just do one more. Let's find the length of just the parabola y equals x squared from 0 to 4. Let's find this length. Well, this is y equals x squared. Remember, what we need is y prime. That's pretty easy in this case. That's just 2x. So our length is the integral from 0 to 4 of square root of 1 plus y prime squared dx. 0 to 4 square root of 1 plus 2x squared dx. Integral 0 to 4 of square root of 1 plus 4x squared dx. Now this one is actually a tricky antiderivative. Actually, if you remember on the exam, this is something that we'd actually have to apply using a table of integrals. And we would get a rather complicated antiderivative. At this point, let's just use our calculators and use the numerical integration technique. I'm not going to put this on the screen, but I will just come up with the actual answer. So if we integrate this, you should make sure you know how to get the answer that I'm getting. The answer that I get is 16.819. That is the length. That's not too surprising because when we square 4, we get 16. So um, we certainly expect the length to be around that region anyway, because the height is 16, and then we're moving 4 over, so we're going to get greater than the 16 total length anyway. And so this is a reasonable answer, and we'll take it. All right, and that's all we need to say about 2.5. We'll see you next time.